Hello everyone, welcome to EN4593 Autonomous Systems module. Today we are going to look at the second part of Gaussian filters. Here is the outline. First we will have a recap on what we studied last time. Next we will look at linear Gaussian systems. The main focus for today is the discrete Kalman filter, and after understanding the concepts we will do an example. Finally we will discuss the divergence issues. In the last lecture, we recognized that Kalman filter as the earliest tractable implementation of Bayesian filter for continuous spaces. And it has been used for more than 50 years as a state estimation algorithm. In order to transform the Bayes filter into Kalman filter, we need two things: linear dynamics and Gaussian probability densities. So in the previous lecture, we went through all these supporting material required to formulate the Kalman filter. Now we are ready to look at the Kalman filter algorithm in more details. In a nutshell, we need a linear Gaussian system to apply the Kalman filter. The posterior probability distribution, bel xt, will be Gaussian when three conditions hold. First, we have the state transition model that corresponds to the prediction stage should be linear and its probability density function should be Gaussian. And the second condition is the measurement model that corresponds to the correction stage should be linear and its probability density function should also be Gaussian. And the final condition is regarding the initialization of the filter. So we need a Gaussian distribution as the initial belief bel x0. Okay, so when these three conditions are satisfied, we can apply the Kalman filter to whatever the estimation problem we have at hand. So in other words, if we don't have linear dynamics in the state transition and measurements, and if we don't have Gaussian PDFs, then unfortunately we cannot apply the standard Kalman filter. So you have to be very careful when choosing the right estimation algorithm to your application. Okay. First, let's look at the state transition model. So we should be able to write state transition model in the following form. That is, we have xt equals atx t minus 1 plus bt ut plus epsilon t. So here these are state vectors at t minus 1 and t. Then here we have the control vector, and this is Gaussian noise. Okay, so altogether we have linear dynamics. Now the uncertainty in state transition is given by this epsilon random vector. So it has a multivariate Gaussian distribution with zero mean and RT as the covariance matrix. So this one is Gaussian zero mean and RT as the covariance matrix. Okay. So when I say covariance matrix, now I hope you understand what it means, right? Now let's say there are n state variables. Therefore, we would have xt equal to x1t, x2t, and xnt. Okay, so this is n by 1 vector. Okay, and we can have m control inputs. So that means ut would be u1t, 2t up to mt. Okay, so this is m by 1, and the rest of the matrices, so A will be n by n matrix to be compatible with the above equation. Then B would be n by m matrix. Okay, so the uncertainty in state transition is given by this epsilon vector. Okay, so if you want to use Kalman filter in your application, the first thing you should check is whether you can write the system dynamics as given in this equation. Okay. Similarly, if we look at the measurement model, we should be able to write it in the following form. So we have zt equals ct times xt plus delta t. The uncertainty in measurement is given by the delta random vector. So it has a multivariate Gaussian distribution with zero mean and qt covariance matrix. So this one is Gaussian with zero mean and qt covariance matrix. Okay. If our sensor gives us k readings about different aspects of the system, then we can write zt as a k-dimensional random vector. Okay, so this would have z1t, z2t up to zkt. So this is a k by 1 vector. The C matrix will be k by n matrix. Okay. So again, if you want to use Kalman filter in your application, the second step would be to write the measurement model as described in this equation. Understood? Alright, now we can have a look at the discrete Kalman filter algorithm. We will not derive the equations as I mentioned before, but that will not stop us from understanding the internal workings of the algorithm. Okay. With linear models and Gaussian probability densities, we can transform the base filter to the Kalman filter using a probabilistic approach. So here we use linear models with Gaussian densities to transform the base filter to the Kalman filter. Actually, Rudolf Kalman used the least square approach in his original derivation instead. So even at the first look at the Kalman filter algorithm, we can see a lot of correspondence between the base filter and the Kalman filter algorithm. So if we check the inputs, we see we have the control input ut here, and then we have the measurement zt, and here we have it in the base filter, and the previous belief. So bel x t minus 1 is the previous belief in the base filter, and in the Kalman filter we have the same thing in the form of Gaussian. So the previous estimate is given by a mean mu t minus 1 and a covariance sigma t minus 1. Okay, so similarly, if you look at the output, in base filter we have bel xt, and in Kalman filter we have mu t and sigma t, which is again the same thing in Gaussian world. Okay, now the first step in the base filter gives us an intermediate belief given by bel xt bar. Okay, and if you look at the Kalman filter in line 2 and line 3, what do we have? So here again we have mu t bar and a sigma t bar. Okay, so this is pretty much the same thing as the base filter. So this part in the Kalman filter basically gives us bel xt bar. Alright, so it's pretty much the same. Even though we are not going to derive the Kalman filter algorithm, it's not difficult to understand the expression for mu t bar. That is, if we look at this one in line 2, and if we look at the linear dynamics in the state transition model, so here we are actually trying to get a mean, okay, for the state transition. And from what we studied in linear dynamics in the previous lecture, can you find out what the mean of this when noise is Gaussian? So you can see that mean of this guy would come from AT times mean of this guy, and here we actually assume this to be constant throughout that time step. So this will appear as it is in the Kalman filter here. And what about the noise? So it is zero mean, right? So there won't be any contribution to our mean, right? So simply we have our first line automatically derived. Okay. Next, if you can remember, when we discussed Gaussian distributions, transform through a linear system, how did the covariance transform? So if you recall that, we would have sigma t bar given by AT and the covariance of this guy, that is sigma t minus 1, okay, times AT transpose. Okay, so that's the covariance coming from this part, and again there is no uncertainty in this part, therefore there is no variance or covariance to be included in this expression. And finally, for the Gaussian noise, we have R. Okay, so that appears in this expression, right? So we can easily find an expression for sigma t bar as well. Okay. Next, we have something called the Kalman gain, right? So this one is known as the Kalman gain. Okay. And in lines 5 and 6, we can see the ultimate result again in the form of two parameters, mu t and sigma t. So that basically corresponds to bel xt in a Gaussian world, right? So this is simply bel xt. So I hope you saw the correspondence between the base filter and the Kalman filter, right? So initially we have bel xt bar in the form of mu t bar and sigma t bar. Then we have some intermediate term called the Kalman gain, and finally we have bel xt in the form of a Gaussian again with mu t and sigma t. Okay. Now if we look at line 5, we call this term as the innovation. Okay, so this is innovation. So what is special about this innovation term? So it is the difference between the actual measurement ZT and the predicted measurement. That is, so we take the intermediate result mu t bar, this one, and use the measurement model. Here we have the measurement model. So we create a measurement. So here we can see we have created a measurement, or we have predicted a measurement. Okay, so this term is actually a predicted measurement. Okay, so in the innovation, what we do is we compare the actual measurement that we obtain and a predicted measurement. All right. So next, we are going to look at what Kalman gain K is. Okay. To understand that, let's take a simple example. Let's say we have two informations, A and B, and we want to fuse them to obtain a better estimate. Now if both A and B have equal uncertainty, then it is not wrong to take the mean of A and B as, let's take that as C. So this is A plus B over 2, where A is information 1 and B is information 2. Okay, so we are trusting A and B equally. Therefore, when we put those two information together, we can get a better estimate, right? Now, instead of this one, I can also write the same expression as A plus half B minus A. Do you agree with that? So when we look at it, we have A and minus half A, which is half A, and then we have half B. Okay, so it's the same thing. So here I have used half when both A and B have equal uncertainty, right? A, B have equal uncertainty, and there's nothing wrong with that, right? Now instead of the value half, if I put K there and constrain K within the range of 0 and 1, what do we understand from that? So let me write it here. I have A plus K instead of half times B minus A. So what do you understand from that expression? So we can see when K is 0, so this whole term disappears, then we have A for C. So that means we are totally trusting A, right? So let me write it here. And K equals 0, we totally trust A. And similarly, when K equals 1, what do we get? Then A will disappear from the expression and we have B, right? So when K equals 1, we totally trust B. Okay. So with other K values between 0 and 1, we are basically giving a weight of contribution to each information A and B, right? So even though it is not exactly what we have here in the Kalman gain, the idea is the same. Okay, so the Kalman gain is the degree to which the measurement is incorporated into the new state estimate. Okay, so here we have two information, one coming from state transition, the other one coming from the measurement. So we have to fuse them. So when we are fusing them, we have something called the Kalman gain, and this is actually the optimal gain that we can think of fusing the two information. Understood? Without a proof, I mentioned that the expression we have for the Kalman gain here is the optimal gain to fuse the two information we have. Okay. Now if we take a one-dimensional scenario and let Q, which is the measurement noise variance, be very large. Okay. So when there is too much noise in the measurement, this term would be very large, and here we have the inverse. Therefore, the Kalman gain would be very small. Okay, so let me write that here. So, for example, 1D scenario, and say Q is large. Okay. high uncertainty for the measurement. Okay, then as I said before, k will be small, right? So this is from line 4. So what do we understand from that? Now if we look at this line, okay, now we have a very small Kalman gain. So it says that the resulting mu t would be close to mu t bar, because the measurement noise was very large, so the contribution from the measurement is going to be small because kT was small. Therefore most contribution now comes from the system dynamics. Okay, so our mu t will be close to mu t bar. So this is just one scenario I explained out of many different scenarios we can face in a real system. Okay, let's visualize what happens in the Kalman filter for a one-dimensional robot localization problem. Let's say our predicted estimate mu t bar and sigma t bar give this Gaussian distribution. Okay, and from the measurement we have this second Gaussian distribution, and it is evident that the sensor is kind of accurate as the spread of the Gaussian is small. So this is the measurement. Okay, and for the time being let me call this as the prior. So in the correction step in the Kalman filter, we fuse these two together and obtain the better estimate as given by this dark Gaussian distribution. Okay, so this one is after combining prior and measurement. So this is happening in the algorithm 4 to 6 line. Okay, now there are two things to note. First is the uncertainty of the resulting Gaussian is smaller than both the input Gaussians. Okay, so let me write that. The uncertainty is smaller than both. The second thing we notice is the mean of the result is in between both the means of the input Gaussians. So the mean is in between both. Okay, now if the robot moves to the right, the uncertainty will grow and our prediction step of the Kalman filter will give something like this Gaussian distribution. So this happens when the robot moves and we have a state transition, and in the algorithm it is on the lines from 2 to 3. Okay, and we see that the uncertainty grows. Okay, now we will take another measurement. So this is the second measurement, and once both these Gaussians are fused, we will get a resulting Gaussian like this. So again, you can notice the two observations where the mean of this resulting Gaussian happens to fall in between the means of these two, as well as you can see the uncertainty of the resulting Gaussian is smaller than this one and that one. Okay, so I will write that uncertainty smaller than both. Okay. In the Kalman filter algorithm, we can actually have mathematically equivalent expressions for covariance sigma t and the Kalman gain kt. However, they can differ numerically when we actually calculate it due to finite precision arithmetic. So for the Kalman gain, we can have this expression instead of the one we already had. Okay, but you can see that this one contains sigma t, which is an output. So sigma t should be also calculated differently without using the Kalman gain. Okay. The posterior state covariance can also be calculated differently, but it is a little bit involved than what we already had. The first expression is actually computationally simpler, but it has a problem. It does not guarantee symmetry or the positive definiteness when we are using finite precision arithmetic. The second expression is known as the Joseph stabilized version, which is more robust and stable than the first expression. The good thing about it is that it also guarantees symmetry as well as positive definiteness as long as sigma t bar is symmetric and positive definite. Okay. Another interesting observation of the Kalman filter algorithm is that we actually don't need to calculate everything real time. For instance, the uncertainty of the filter can be known even before we run the system. Now if we look at line 6 here, we see that sigma t depends on k, c and sigma t bar. Similarly, if we take sigma t bar, it depends on a, r and sigma t minus 1. Also, the Kalman gain kt depends on c, q and sigma t bar. Okay, so when we initialize the filter with certain sigma 0, all the sigmas and k's can be known for the future. So they can be stored in memory, which is a good thing for embedded systems. Okay. As a result, we can know the performance of the filter in terms of uncertainty before the system is run. So why do many researchers and engineers prefer the Kalman filter and use it as the workhorse for state estimation problems? Well, it can be mathematically shown that it is the optimal state estimator for linear Gaussian systems. Okay. By the way, do you know the meaning of the word optimal? Because it's a word you should be very careful with if you use it in any of your academic writings. So optimal means the best possible, okay? And you cannot just say it without mathematically proving that it is the best possible way. So be careful when you write your final year project reports or research papers with the word optimal. All right. Even though the standard Kalman filter is the optimal state estimator for linear Gaussian systems, and it is very attractive as well, we might not be able to use it unless we have these two models satisfied. That is, we should have linear Gaussian model for state transition, and we also have a linear Gaussian measurement model as well. Okay, and finally, the Kalman filter extracts the maximum information possible from the sensor readings for state estimation. In fact, it is why Kalman filter is the optimal estimator. Okay. To reinforce what we learned so far, let's do an example. Let's say we need to build an autonomous target tracking system. So we basically need to estimate the location of the target. So here is our target, and let's say this is our autonomous system. We can have a coordinate frame like this. So for simplicity, let's assume we are dealing with 2D. Okay, so these coordinates are x, y. So we need to estimate x and y. So what is the very first thing we need to do? We need to identify the state variables. Now, since we are interested in finding x and y location of the target, our natural choice should be to have x and y as state random variables. Okay, so first I will try having x and y as state variables. And in terms of the Kalman filter, our first goal is to use this state and formulate the state transition model in the form of this equation we have here. Okay, one quick question. Is there any control input we need to consider? Well, the tracking system is a passive system, right? So it does not give any control inputs to the targets to move. It would be strange if it does that, right? So the targets move arbitrarily and the autonomous tracking system has to passively track the target without giving the target any control inputs. Okay, so for this the answer would be no. The next question is the state we have chosen a complete state? Or in other words, can we predict the next state using the current state? Now here we don't have to consider control input, as I said before, because there is no control input that the target tracker gives to the target. Okay, so what do you think? Well, apparently it is difficult to predict the next state with the chosen state variables, right? So the answer to this question is also no. So that makes us to rethink about the state, because this state is not a complete state. And if our state is not a complete state, all our assumptions, including Markov assumption, would make no sense, right? Okay, let's think of some improvisation. How about we include velocities as well? So my second option is the state x having x, y, x dot, y dot. Okay, now can we predict next state using current state? Well, if we assume that the target moves with constant velocity within the time step, then we have a good chance of tracking it, right? So we are not saying that it should move at constant velocity all the time, but within the time step. Okay. So with that assumption, we can assume that we can predict the next state from the current state, and therefore our state is complete, right? So our assumption is, if we assume that the target moves with constant velocity, then yes. Okay. All right. Now shall we write down the equations for state transition? Of course, we have done a similar example when discretization was introduced, but actually there is no need to start with the continuous time equations and transform them into discrete time, even though that's the first principle or the correct way to do it. We can instead straight away write down the discrete time equations. Shall we do that now? So with the constant velocity assumption, we can write xt equals xt minus 1, the previous position, plus delta t times velocity in the direction and the noise component. Okay, and similarly we can write yt equals yt minus 1 plus delta t times yt minus 1 dot plus the noise component. And what about the velocity? So we are assuming constant velocity model, therefore we would have something like this. So this is the noise component for the velocity. So the next velocity in the next time step is the previous velocity plus some noise component. So there's a sudden jump. So that's how different velocities are achieved, right? And yt dot would be yt minus 1 dot plus the noise component. Understood? Now can you identify the A matrix? So if you look closely, we can find A matrix to be zero, zero, 1, 0, 0, 0, 0, 1. Okay, got it? And again, there is no control input in this example, so there is no B matrix that we need to consider. So I will write that as ut equals 0 vector, and B can be anything, so we can have B equals 0. Okay, so what you need to remember is that the target tracker does not give any control inputs to the target, so in this application this term is not there. Okay, next we are going to discuss the measurement model. For this example, let's assume a hypothetical scenario where we have a position sensor that tells us the XY coordinates of the target. Of course, this is an impractical situation because we should track the target without the target having a GPS-like sensor telling us where it is. But let's proceed with that assumption only for this example to understand the Kalman filter implementation. Okay, so the measurement would be two-dimensional random vector. We can have it as zt equals, let's say, zx and zy transpose. Okay, now our task is to model this measurement in linear Gaussian manner, as in this equation. Can you try to do that now? Okay, so on the left hand side we have zx, zy, then we need a C matrix, and our state was xt, yt, xt dot, yt dot. Okay, and there is some noise in the measurement as well. So this is our C matrix, right? And what goes in there? So if you did that correct, you would get 1 0 0 0 0 1 0 0. Understood? So only two aspects from the state is covered by the sensor, the x position and y position, and in fact it's okay because we are the ones who included the velocity variables, right? We only wanted to know x and y. We have completed two steps, and the final step is to initialize the filter. The most natural case is that the autonomous target tracking system has no idea about the initial position of the target. That means the whole XY plane can be equally probable, right? So here is a proposition. So we don't know the initial position of the target. Let's use a uniform distribution because the target can be equally anywhere in the space. What do you think about that? Yes, no, maybe, no idea. Of course, no. Everything should be Gaussian. Remember? So let me write it here. Everything should be Gaussian. Okay, so this is no. So we should have some initial mean for the Gaussian. And what about the initial state covariance? Since we have no idea whatsoever, how about we use sigma naught as infinity on the diagonal and 0 for the off diagonal. Or maybe let's call this as ki, where k is a very large number. So that tells us there's very high variance for the individual entries on the diagonal, since the initial position is not known, and we don't know any correlation between the state variables. Therefore, the off-diagonal terms are 0. Okay. Now we need a mean, right? Here is another proposition. Let's use the first measurement and create a Gaussian from that. Yes, no, maybe, or no idea again. Well, in fact, it is a most commonly used technique in practical implementations. Right, so this I would go with maybe. This is one way of initializing the Kalman filter. Okay, so when you practically implement a Kalman filter, now we have some tips how to initialize the filter. Okay, there can be rare situations where we might know the initial position. In that case, if I ask you to populate sigma naught or the initial state covariance matrix, how would you do that? We know the initial position means there is no uncertainty, right? Then we can have sigma naught equals the zero matrix. So the individual variances along the diagonal are 0, as we are certain about the initial position, no uncertainty there, and the correlation between state variables are also 0. Okay. All right. So implementing the Kalman filter simply means identifying the required matrices, populate them at each time step, and evaluate the lines through 2 to 6, and that's it. Okay. So by now we have U, the control input, Z, the measurement, the previous mean and covariance, or the initial mean and covariance if it is the first time step. Okay. Next we identified A and B. So we have A and B as well. Actually, in this example there is no B and U, right? Then we also identified C matrix. Okay, so we only miss R and Q. So we need R and Q, which are the process and measurement noise covariances. Okay. Actually, R and Q are a little bit difficult to obtain. Now if I start with the Q matrix, the measurement noise covariance, it is relatively easier than R matrix. For the Q matrix, what we need is the characteristics of the sensor. So this would depend on the sensor. Okay. Usually that information can be obtained from the datasheet itself, right? So we will use sensor specifications to populate Q matrix. So if we take a GPS sensor, for example, it would tell us the standard deviation of the measurement we get. So the standard deviation of X measurement and the standard deviation of its Y measurement. Okay. Therefore, we can put those values in the diagonal, and unless it is explicitly mentioned, we are going to assume that there are no dependencies between X and Y readings. Right? So we will use 0 for the off-diagonal terms. So we would have something like this, and 0, 0. So this is a 2 by 2 matrix. Okay. Of course, we can do some experiments as well, collect enough data and find these statistics ourselves and use them in the Q matrix. Okay. Now, the process noise covariance is not that easy to obtain. Again, the best way is to conduct enough experiments to find the process dynamics. So this depends on process dynamics. Okay, and let me also write that it is usually difficult to obtain. Okay, for example, let's say we give some motion command to a robot. So that's our control input. So with this motion command, let's say we give 5 centimeters per second velocity command. So after 1 second, it should be 5 centimeters away from the previous position, given ideal conditions. But we can do the experiment enough trials to see how much it deviates from the expected motion, right? And we can use that information to find the required terms of the R matrix. Understood? So let's say we can use experiments to find the R matrix, and for this particular example we would have a 4 by 4 matrix, and maybe our parameters would be alpha 1, alpha 2, alpha 3 and alpha 4, the rest being 0. Okay, let's see Kalman filter in action in this video. The black square shows the measurements, which are very noisy in this case, and the red one shows the actual trajectory of the target, and the green one shows the Kalman filter output. Let's have a look. So you can see how noisy the measurements are and how the Kalman filter tracks the target nicely. Here is another example. So when you are working with machine vision, there should be other algorithms to actually detect the object and generate an observation for the Kalman filter, because Kalman filter itself cannot do it alone. It is not meant for that purpose. So here we have a camshift algorithm which detects the object and it generates an observation to be used in the Kalman filter. Okay, let's have a look. Did you notice something interesting? Let me play that again. Okay, now the question is, how did the object got tracked even when it was occluded by the paper? Any thoughts? Well, if you can recall, the Kalman filter has two stages, the prediction and the correction. So when there are no measurements, only the prediction step is in charge. So it keeps on predicting even when it is not getting any measurements. So as long as there is no significant change in velocity or a change in moving direction, the Kalman filter is able to still track the object even when it is occluded for a small period of time. But you should know that it is not guaranteed and the filter can actually diverge as well. That brings us to the topic of filter divergence. From all what we have seen, Kalman filter seems to be a very attractive algorithm for state estimation. But does that mean it is perfect? Well, theoretically it is perfect for linear Gaussian systems, but when we implement it on a real system, there is possibility that it will not work as expected. And there are two main reasons for that. The first one is finite precision arithmetic. Even with a good computer, there can be situations where the filter may diverge or become unstable when implemented for certain applications. The other primary cause is the modeling error, which is more common. When we implement Kalman filters, we do a lot of assumptions. We consider that the system model we have is precisely known, and the matrices A, B, and C are known exactly. Also, we assume that noise is zero mean, Gaussian, and completely uncorrelated. So it's very easy to understand that in a real implementation, there is a lot of chance that Kalman filter can go bizarre and divert to give very poor results. There are some basic strategies we can use to improve the Kalman filter performance. We can increase arithmetic precision. We can try to use fictitious process noise. And we can also try to symmetrize covariance matrix at each time step. And we can also initialize covariance matrix appropriately to avoid large changes. Now it is important to note that the effectiveness of these strategies depend on the application, and we need to do simulations or experiments to check for the validity. If our Kalman filter implementation is on a PC, then increasing arithmetic precision is simple. Just change the variables to double precision. Such a simple step can even help changing a diverging filter to converge. Right? However, it may not be feasible to increase arithmetic precision on a microcontroller implementation. Or in fact, implementing a Kalman filter on a microcontroller may not be feasible at all, because there exist operations such as matrix inverse. Now another strategy we can employ is to use fictitious process noise. So what this means is that we are going to naturally believe that the process dynamics has more noise than the measurement process. And as a result, we are going to inflate the variances in the process noise covariance matrix. Okay, so we are basically telling that we have less confidence in the system model when compared to the measurement model. Being overconfident or overly optimistic about an estimate will be disastrous, but its opposite should be fine. And that's why we usually don't try to obtain exact error statistics of system dynamics, but instead use some reasonable values. Okay? If you can remember, we previously discussed about other forms of Kalman filter that ensure symmetry and positive definiteness for covariance matrices. If that does not work with finite precision arithmetic, we can try techniques like forcefully making it symmetric as given here in this equation. Right? We take the covariance matrix and get the transpose of that, add them together and divide by 2. Okay, a simple technique. Another way is to force the terms below the diagonal to be equal to those above the diagonal. Alright? So these are easy solutions we can try to improve the filter because they are straightforward. But you have to remember that if we have significant modeling errors, then these tricks would not really be helpful in recovering a poorly performing Kalman filter. With that, we have come to the end of this lecture. Let me summarize what we learned. Kalman filter is the optimal state estimator for linear Gaussian systems. So if we are to employ the Kalman filter to our application, we should make sure we have linear Gaussian state transition, linear Gaussian measurement model, and Gaussian initial belief. We saw that some terms of the Kalman filter could be computed offline, and it is helpful especially for embedded systems. We looked at a target tracking example to understand how we can use Kalman filter in an application. Finally, we realized that we may experience issues in convergence as well as performance when Kalman filter is used in real applications. Thank you.